Alright, in this video we are going to be looking at stationary points. So we're going to learn how to find these stationary points and how to also determine their nature. Which is to say, is this a minimum point or is this a maximum point? So if you've got the graph of, for example, let's draw a Cartesian plane. This is the y-axis, this is our x-axis. So say we've got this graph. Say this is y is negative x squared plus 5, for example. The turning point is this point over here. And so in this case, we can tell that this is going to be a maximum point. Alright, but that's because we have sketched the diagram and we can see from the diagram that it's clearly going to be a maximum point. We are going to use differentiation to first of all find the coordinates of this stationary point and then to also determine whether this is a maximum point or a minimum point using just differentiation. We're not going to be sketching diagrams. So differentiation can also be used to locate the stationary points for other functions. And so obviously for a quadratic, because we know how to sketch a quadratic function, it's very easy for us to just sketch a diagram and look at the diagram and evaluate and determine whether this is a maximum or a minimum point. And to get the coordinates of that stationary point, we can just complete the square if it's a quadratic. But for other functions, it's not so straightforward. So the way to do that is through differentiation. So when you find the first derivative of a function, that's going to be dy dx. This here is known as the gradient function. Whatever you get here is what we call our gradient function, dy dx. So it generates the gradient at a particular point. So at a stationary point, the gradient, for example, at this point here, the gradient is going to be 0. So at any stationary point, whether maximum or minimum, dy dx is going to be equal to 0. Alright, and so this is the main idea we will use in finding stationary points. Then to be able to determine whether our stationary point is a maximum point or a minimum point, we then use our second derivative, d squared y dx squared. Alright, we substitute our x value into the second derivative, and if the second derivative is positive, it means our stationary point is a minimum point. However, if it's negative, then we've got a maximum point. Alright, so these are the ideas we're going to be using to first of all find the coordinates of our stationary points and then secondly determine their nature. So let's look at some examples and apply all of this information. So we're given that the equation of a curve is y is equal to 54x minus 2x minus 7 cubed. Part A says find dy dx and d squared y dx squared. So we have to find the first and second derivatives. We've been given y is 54x minus 2x minus 7 cubed. Let's start by finding the first derivative dy dx. So we're going to differentiate 54x. If you differentiate 54x, you get 54 minus, then we're going to differentiate negative 2x minus 7. And so if you prefer, you can use the substitution to say let u equal to x minus 7. But here I'm just going to assume that you understand the intuitive way of thinking about it. If you still struggle with it, make sure to go back to the previous video on the chain rule. So we start by differentiating our outer function. So bring down the 3 multiplied by 2x minus 7. Subtract 1 from the power, so 3 minus 1, that's 2. And then now we differentiate the inner function, 2x minus 7. If you differentiate 2x minus 7, you're going to get a 2. So this means dy dx is equal to 54 minus 3 times 2, 6, 2x minus 7 squared. This is our first derivative dy dx. Now we need to find our second derivative. So to get the second derivative, d squared y dx squared, you just differentiate your first derivative. So if you differentiate 54, which is a constant, you're going to get 0. So we've got negative 6, and then here bring down the power 2. then we've got 2x minus 7, subtract 1 from the power, so you get 2 minus 1, which is 1, multiplied by differentiate 2x minus 7, so 2. So d squared y dx squared is equal to negative 6 times 2, negative 12, times 2, that's negative 24, times 2x minus 7. Alright, so we've got our first derivative here and our second derivative there. Part B says to find the coordinates of each of the stationary points on the curve. So we said we know that the gradient at a stationary point is equal to 0. This is the idea we use in finding coordinates for stationary points. So we're going to equate our expression for dy dx to 0, which is this 54 minus 6 times 2x minus 7 squared is equal to 0. Notice how this is a quadratic and completed square form, so we can solve this quadratic equation using the completing the square method. So let's move this term to the right so that it becomes positive. That's 6 times 2x minus 7 squared is equal to 54. Divide both sides by 6. 2x minus 7 squared is equal to 9. Take the square root on both sides. Remember, this is going to be plus or minus, so that becomes 2x minus 7 is equal to plus or minus 3. So 2x is equal to 7 plus or minus 3, and divide both sides by 2. So x is equal to 7 plus or minus 3 over 2. And so x is either equal to, let's start with the negative 1, 7 minus 3 over 2, that gives us x is equal to 2, and then we've got x is 7 plus 3 over 2, so that gives us x is equal to 5. Alright, perfect. So these are the x coordinates for our stationary point. They want the coordinates, so we have to find the y coordinates as well. So to get the y coordinates, we use the equation of the curve. So that's y is 54x. Y is equal to 54x minus, that's 2x minus 7 cubed. 2x minus 7 cubed. So let's start by evaluating the y coordinate at x equals 2. That's going to be y is equal to 54 multiplied by 2 minus 2 times 2 minus 7 cubed. So y is equal to, let's punch this into the calculator, 54 times 2 minus 2 times 2 minus 7, and this is cubed. That's 135. So the coordinates here are 2, 135. And then at x is equal to 5. Substitute into the equation of the curve, that's 54 times 5 minus 2 times 5 minus 7, and this is to the power 3. So y is equal to, let's punch this into the calculator, 54 times 5 minus 2 times 5 minus 7, and this is to the power 3. We get 243. So this gives us the coordinates 5, 243. So these are the two stationary points. These are their coordinates. So now part C says determine the nature of each of the stationary points. So to determine the nature of our stationary points, we use our second derivative. So we're just going to rewrite our second derivative here. D squared y dx squared is equal to negative 24, then 2x minus 7. Let's just check to make sure that's correct. Yes. Alright, so at this stationary point x is equal to 2, so let's substitute x with 2 in our second derivative. So negative 24 times 2 minus 7. So let's punch this into the calculator, negative 24 times 2 minus 7, and this gives us a 72. So at the point 2, 135, our second derivative d squared y dx squared is equal to 72, which is greater than 0. So it means it's positive. It means that this here is going to be a minimum point. Minimum point. So let's do the same for x is equal to 5. That's going to be negative 24 times 2 times 5 minus 7. Punch this into the calculator and you get negative 72 instead. So negative 72. So add, that's 5 to 43. You get that the second derivative d squared y dx squared is equal to negative 72, which is less than 0. So hence maximum point. Alright. And so we've determined the nature of our stationary points. Alright, let's look at another example. Here we're given that the equation of a curve is y is equal to 3x plus 1 minus 4 times 3x plus 1 to the power half for x is greater than negative 1 over 3. Part A is find dy dx and d squared y dx squared. Alright, so our equation is y is equal to 3x plus 1 minus 4 times 3x plus 1 to the power half. Okay, so let's start by finding the first derivative dy dx. If you differentiate 3x, you get 3. If you differentiate a constant, you get 0. Then we've got minus 4. So here, differentiate the outer function first. So bring down the power 1 over 2. Then we've got 3x plus 1. Subtract 1 from the power, so half minus 1, which gives us negative half. And now differentiate the inner function. So if you differentiate 3x plus 1, you get a 3. So dy dx is equal to, this is 3 minus 4 times half is 2, so 2 times 3 gives us 6, times 3x plus 1 to the negative 1 over 2. So this here is our first derivative, dy dx. Alright, so let's find our second derivative. So d squared y dx squared is equal to, if you differentiate a constant, you get 0. Then we've got negative 6. Let's differentiate the outer function first. So bring down the negative 1 over 2. Then we've got 3x plus 1. Subtract 1 from the power, so negative half, negative 1. That gives us negative 3 over 2. And then differentiate the inner function, 3x plus 1. You're going to get a 3. So d squared y dx squared is equal to, so we've got negative 6 times negative half, that's going to be 3, multiplied by 3, that's 9, times 3x plus 1 to the power negative 3 over 2. So this is the first derivative and this is the second derivative. Now part B goes on to say find the coordinates of the stationary point and determine its nature. So again, to find the coordinates of the stationary points, we use the idea that dy dx is equal to 0. So we're going to equate the expression that we have for dy dx here to 0. So that's 3 minus 6 times 3x plus 1 to the negative half, and this is equal to 0. And to solve this, I'm just going to rewrite our 3x plus 1 to the negative half with a positive power, so that is easier to solve. So that's 3x plus 1 to the power 1 over 2, and this is equal to 0. So we want to start by getting rid of our denominator. To do that, let's multiply through by 3x plus 1 to the power half. So that becomes 3 times 3x plus 1 to the power half minus 6 is equal to 0. Okay, so now we need to solve for x. So to do that, add 6 to both sides. 3 times 3x plus 1 to the power half is equal to 6. Divide both sides by 3. 3x plus 1 to the half is equal to 2. And now to get rid of the power half, square both sides. So this becomes 3x plus 1 is equal to 4. So you get 3x is equal to 4 minus 1, which is 3. So you get x is equal to 1. Alright, so this is the x coordinate for our stationary point. To get the y coordinate, we use the equation of the curve. So we're going to substitute x with 1. So y is equal to 3 times 1 plus 1 minus 4 times 3 times 1 plus 1 to the power 1 over 2. So y is equal to, let's punch this into the calculator, 3 times 1 plus 1 minus 4 times 3 times 1 plus 1 to the power 1 over 2. And this gives us y is negative 4. So it means the coordinates of our stationary point are 1, negative 4. But we were also instructed to determine the nature of this stationary point. So to do that, we're going to use our second derivative over here. So substitute x with 1. So 9 times 3 times 1 plus 1 to the negative 3 over 2. Punch this into the calculator. 9 times 3 times 1 plus 1 to the negative 3 over 2. This gives us a positive 9 over 8. So at the point 1, negative 4, our second derivative d squared y dx squared is equal to 9 over 8, which is greater than 0. Hence, we have a minimum point. And that's going to be our final answer. Alright, so that's it for the stationary points video. Make sure to go through the quiz and I'll see you in the next one.